So first of all, let's think about what we need in order to get an equation of a plane, or what determines a plane. Like, how much knowledge do I need to have in order to be able to say what a given plane is? So one thing that I need to know is how is this thing slanted, right? It's like in a line in 2 dimensions. How is it slanted? Do you have any ideas about how we can say how this thing is slanted? How we can describe that?
A little bit to the right.
Say it.
A little bit to the right.
A little, okay. You can describe it. It looks like it's landing down to the right, something like that. How do you think we could describe it, like with an equation, or in terms of the math that we're used to? For example, with a line, how did you describe how a line was slanted in 2 dimensions?
Slope.
Yeah, good. We had a slope. So it would be cool if we had a slope for this. But the problem is that if we just have a number for a slope, it doesn't tell us in which direction it's slanting. Like in 2 dimensions, if you have a number, that tells you how steep it's slanting and what do you need in order to say the direction in 2 dimensions. Because there is more than one possible direction for a given number, a given slant. But the way we handle that, I'm thinking of positive and negative. If it's positive, it goes up. If it's negative, it goes down. Here, you can have up, down. You can have slanting in, a lot of different directions. So we need a different way to do it. Has anything popped into your mind of possible ways that we could do that? Okay, good. If I have a vector that's perpendicular to this plane, like let's say this is the plane. If I have a vector perpendicular to the plane, that tells me exactly how the plane slants. So this is something that, is hard to come up with if you're only thinking about an analog from 2 dimensions. If I move the plane around, then the vector moves with it. If I move the vector, the plane has to move with it. So just having one normal vector does tell me exactly how the plane slants. But I could have this plane, or I could have this plane. Any plane that's parallel to this one has the same normal vector. So what else do I need to be able to say this specific plane? Yeah, I need 1 point on the plane. So this is also like a line in 2 dimensions. You needed 1 point on the line, then you needed the slant. So let's say that we do know a point. Let's call it x naught, y naught, z naught. Some fixed point that's given to us. And let's say that we do know a vector that's perpendicular to the plane. I use n for normal vector. And let's just say the components are a, b, and c. And if I'm given those 2 pieces of information, I should be able to come up with an equation that describes this plane. So in other words, I should come up with an equation that involves x, y, and z, so that if I take a point x, y, z on this plane, it makes the equation true. It gives me the same number on both sides of the equation. If I take a point off the plane, it gives me 2 different numbers. So the way that we can do that is, if I grab a point x, y, z here in the plane, I'm wanting to figure out a way to describe why this is special and that it sits in this particular plane. So one thing I can do is take the vector from the point that we know is in the plane to this random point that may or may not be on the plane. And if this point is in the plane, then what's the relationship between the blue vector and the red vector?
You have no walking time.
Good. They're normal to each other, they're perpendicular, they're orthogonal. So how can we describe that? How can I figure out if they are? Or how can I demand that they are?
Cross product.
Okay, close.
Dot
The
product.
cross product, so if I take the cross product of these two, that will give me a vector that's orthogonal to both of those. But if I take the dot product, whoever said dot product, what specifically do I need to demand about the dot product between the blue vector and the red vector? I would say that they're orthogonal. Yeah, good. I don't think we talked about that explicitly last time, but how do you know that if the dot product is 0, that these two vectors are orthogonal?
It's the magnitude of two vectors times cosine theta.
Okay, good. So let's just say we have two vectors A and B. One of the definitions for this was length of A times length of B times cosine theta. And if they're orthogonal, that theta is 90 degrees, cosine 90 degrees is 0. So these two vectors are orthogonal precisely when this is 0. So if I take this vector and this vector and demand that the dot product is 0, then I get exactly the equation for this plane. How can I write the vector that starts here and ends here?
X at 0, y at 0, 0 at 0.
Okay, good. Take the coordinates of the second point, subtract the coordinates of the first point. To get the vector, I'm demanding that that is 0, and then that is the equation of the plane. So if this is ABC, then the equation this gives me looks like this. And just to be clear, the A, B, and C will be specific numbers that I already know because I know what the vector is. The X naught, Y naught, Z naught will be specific numbers that I already know. They're constants. The only variables here are the X, the Y, and the Z. So if I wanted to, I could multiply all of this out and then combine all the constants together and bring them to the other side. And then that would look something like this. I would have an AX, and a BY, and a CZ. And then everything else, I'm moving to the other side, and I'm just going to group all that together and call it D. So usually, if somebody hands you the equation of a plane, it will look something like this. A, B, or C could be 0. At least one of them will be non-zero because this setup only makes sense if this vector is non-zero. But you could have, for example, 1, 0, 0, and then this would say X equals B. What would this equation look like if this plane was just flat, just horizontal, parallel to the XY plane?
Z equals 0.
Z equals 0.
Okay, good. It would say, okay, the equation of the XY plane itself is Z equals 0. And then anything parallel to that, like if it goes up, it would be Z equals some constant. All the points on the plane could be described by Z equals the same number. Good? And I just want to go through one example. So let's say that instead of being given a vector like this and a point in the plane, we're given 3 specific points. So I'm going to put 3 points on there, and then I'll write down what they are over here. Let's say we've got 1, 2, 3, 0, -4, 5, and 2, 1, 0. If I know 3 points in the plane, that should determine what the plane is. Like if I only had 2 points in the plane, that would give me just this line. And there are infinitely many planes that contain that line because I could take this plane and spin it around this line. That would give me infinitely many planes containing the line. But if I add a 3rd point, that tells me exactly what the plane is. So we should be able to get the equation of the plane from these 3 points alone. You guys have an idea of how we can do that?
You find the vector of point one and point two, and then point one, point three, and then multiply.
Okay, so I know I heard find a couple of vectors like that, and then you said to do what with those two vectors? Okay, good. If I take their cross product, remember that gives me a vector that's orthogonal to those two. So this is vector A, vector B, take A cross B. Sorry for using the same letters for vectors and for constants in the same picture. All right, so let's do that. Does it matter which points I use for this? Or can I just take two vectors between any of the points randomly?
They need to start the same. They need to start the same.
Okay. So if I make sure and fix one point and make them start there, then it will definitely work. But what if I took like this vector and this vector? So I have the top blue vector and then the black vector. If I take the cross product of those two, what do I get? This may help. We can take this vector and just slide it over. So we can take this vector and move it over. It's still the same vector. Remember, a vector is just a magnitude and what is it? A magnitude and a direction. So this is still the same vector. Now if I take the cross product of this, the blue vector, it still gives me a vector that's perpendicular. In fact, it gives me the exact same vector. It has the same length too, because this parallelogram. Wait, is that right? Does this parallelogram have the same length as, the same area as this parallelogram? Yeah, it does, because the base has the same length and the height has the same length. So it would actually give me the exact same length. It doesn't matter if they're the same length for the purposes of the equation of a plane. As long as it's parallel to this vector, it would work. We could also get something that points in the opposite direction, but that also would give us the equation of a plane. So intuitively, you may think that you need to pick these points in a specific order. That makes sense. But if you think through it a little bit more, you can take any two vectors here and just take the cross product. So I will go ahead and start with one particular point and take the vector from here to here, and then the vector from here to here. That just makes it a little bit easier for me. So the vector from here to here gives me 0, minus 1, -4, minus 2. And by the way, please make sure I'm doing this correctly, because I often add and subtract incorrectly, especially at the board. So I need you guys to check me. 5 minus 3 is 2. And then going from here to here, I've got 2 minus 1, 1 minus 2, 0 minus 3. So these would be two vectors that sit in the plane, and now I just need to take their cross product. To take their cross product, remember I'm going to think of having an I here, a J here, a K here, and then do the little matrix multiplication that we did last time. So first, for the first component, cover up the first column, and then I've got -6 times -3 minus -1 times 2. -1 times 2 is -2. And then what do I need to do for the second
With a negative sign.
coordinate? Yeah, good. Put a negative sign out in front. cover up the second column, I've got -1 times -3 minus 1 times 2. And then same thing for the last one, cover up the third column, -1 times -1 minus 1 times -6. So that's our vector orthogonal to the plane. And now we just go back to this equation of the plane here. This is my A, so that's 18 plus 2 is 20. And I need to pick a specific point for my x naught, y naught, z naught. I'll go ahead and pick this first one. But it doesn't matter which point I pick. The equation would look a little different, but it would actually be the exact same equation if we simplified it in a form like this. And for example, divided everything by c and solved for z, we would get the exact same equation. So this will be x minus 1. And we got minus 1 times y minus 2. This is 1 plus 6. Times z minus 3. And all of that has to be equal to 0.